So, you know when you look at one of those beautifully organized minimalist kitchens, like the ones you see in architectural
Oh
magazines?
yeah, where everything is just perfectly sleek.
Right, exactly. The counters are completely clear. Everything is tucked away behind these sleek, handleless cabinet doors. It looks incredibly peaceful.
Until you actually have to cook a complex meal in there.
Yes, exactly. You try to cook, and suddenly you realize you have absolutely no idea where, like, the spatulas or the spices are hidden.
Right, because the aesthetics of the space have completely compromised how you actually use it.
Totally. And that tension, that really delicate balance between making systems look clean on the surface and making sure they actually, function reliably under pressure, that is the exact focal point of our deep dive today.
It's such a universal problem, really.
It is. We're looking at this incredibly insightful article by Aaron Rose. It was published on tech-reader.blog, and it's called The Secret Life of Go Hidden Dependencies in Context.
It's a great read.
Yeah, it really is. And it explores this exact dynamic through a very specific software engineering dilemma. So for you listening, I want to set the scene that the article paints.
It's not your typical sterile tech office, right?
No, not at all. We are looking over the shoulders of two developers. There's a senior engineer named Eleanor and her junior colleague, Ethan, and they are working out of this beautiful Beaux Arts library in Lower Manhattan.
Such a great setting.
I know, right? High ceilings, classic architecture. It's the kind of environment where the structure of a code base is discussed with the same reverence as, like, the structure of a building.
Which is fitting for what they're doing.
Exactly. And we are going to see how a really well-intentioned attempt to clean up a workspace can accidentally, well, lay the groundwork for a catastrophic collapse.
And even if you aren't a programmer, this is so relevant.
Oh, totally. Because this deep dive is really about how we communicate requirements.
Mhm.
The danger of hiding important details just for the sake of aesthetics.
The whole difference between what is explicit and what is implicit.
Exactly. Okay, let's unpack this by looking at the trap Ethan sets for himself while he's trying to optimize a Go-based billing service.
Right, so Ethan is dealing with a very real frustration here. It's something anyone working in large code bases understands perfectly.
Oh, for sure. The dreaded function, signature bloat.
Exactly. He is staring at a core billing function, and the signature is just massive. I mean, to simply process a user's bill, the function demands a database connection pool,
Mm-hmm.
a centralized logging mechanism, an external metrics client, and then, the actual business data, like the user ID and the transaction amount.
It's just a lot to look at.
It really is. The cognitive load required just to read the top line of the function is exhausting. So naturally, he wants to declutter the workspace.
Right, so he goes digging into Go's standard library, and he discovers this thing called context.withValue. And to Ethan, this looks like an absolute silver bullet.
It seems like the perfect solution to him.
Yeah, he thinks he hit the jackpot. Instead of explicitly asking for the database, the logger, and the metrics client in the arguments, he updates the code. Now, the function only requires two things.
Just a generic context object and the billing amount, right?
Exactly. He takes all those heavy architectural dependencies and he just shoves them into the context using with value, and then he walks over to Eleanor, incredibly proud of himself.
Well, of course he is.
Yeah, he announces that he has basically solved the dependency problem and achieved perfect minimalism.
What's fascinating here is the psychological trap of clean architecture.
Oh, say more about that.
Well, we frequently conflate visual minimalism with systemic simplicity. Ethan looks at his screen, he sees a function signature that fits on half a line, and his brain interprets that as elegant design.
Right, because it looks nicer.
Exactly.
Yeah.
But he hasn't actually removed a single ounce of complexity from the billing logic. The function still absolutely requires the database and the logger to execute successfully.
It still needs the tools to do the job.
Precisely. He has simply moved those requirements out of the visible contract and buried them inside this opaque container.
Yeah, it's the ultimate manifestation of sweeping the mess under the rug. It's like, well, think of it like looking at a really chaotic workbench covered in specialized tools.
A total mess of a desk.
Right. And instead of building a proper pegboard to organize them, you just sweep everything, like the wrenches, the soldering iron, the multimeters. You just sweep it all into a giant, unmarked canvas duffel bag.
A magic bag.
Exactly. The workbench looks pristine, sure, but when you actually need to calibrate a circuit, you are blindly reaching your hand into a dark bag, just, hoping your fingers brush against the right tool.
And Eleanor recognizes this immediately. She doesn't praise his aesthetic victory at all.
Not even a little bit.
No. She pulls up a chair and identifies this exactly as the magic bag anti-pattern. She warns him that it is one of the most dangerous structural decisions you can make in Go.
Which sounds intense.
It is. And the danger stems from a fundamental misunderstanding of what a function signature actually represents in software engineering.
Right, it's not just a suggestion.
Exactly. A function signature is not just a hint, it is a binding technical contract.
But wait, if I am putting myself in Ethan's shoes right now, I might actually push back on Eleanor a bit here.
Oh.
How so? Well, I would argue that software development heavily values principles like DRY, don't repeat yourself, and reducing boilerplate code.
Sure, those are standard principles.
Right. So if the application is successfully compiling and the logic is executing without any errors on Ethan's local machine, hasn't he streamlined the workflow?
It might feel that way to him.
I mean, other developers no longer have to type out 5 different arguments every single time they call the billing service. They just pass the context and the float. The friction of invoking the function is drastically reduced. Doesn't that make everyone's life easier?
Well, the friction is reduced for the person calling the function, yes. But the cognitive and operational burden is entirely shifted to the runtime environment and to future maintainers.
Ah, so somebody else pays the price.
Exactly. Eleanor counters that argument by zeroing in on the concept of compile time guarantees. You see, Go is a statically typed language. Its primary defense mechanism is the compiler.
Right, the compiler is kind of like the bouncer.
A ruthless auditor, really. If your function contract explicitly demands a pointer to a database connection, and a developer attempts to call that function without providing one, the compiler immediately halts the build.
It just refuses to let the software run at all.
Precisely. The compiler enforces the truth of the contract.
But by moving the database into the context, Ethan has basically bypassed the auditor entirely.
He has intentionally blinded the compiler. The context interface in Go is designed to carry arbitrary values.
Meaning anything can go in there.
Right. Under the hood, with value, stores these items as empty interfaces, which means they lose their specific type identity in the eyes of the compiler.
So the compiler doesn't know what's in the bag.
Exactly. The compiler looks at Ethan's new function call, sees that a context is being passed, and says, okay, the contract is satisfied. It has absolutely no idea that the billing logic inside the function is secretly relying on that context to contain a very specific SQL database connection.
Wow, which sets up the exact testing nightmare that Eleanor uses to dismantle his code.
It's a brutal reality check.
It really is. She asks Ethan to imagine writing an automated unit test for his new, quote-unquote, minimalist billing function. And in a standard Go test, you typically initiate the test by passing context.background.
Right, and context.background yields an entirely empty context.
Yeah.
It is a completely bare, freshly instantiated container with 0 values inside of it.
So the test essentially hands the function an empty canvas duffel bag.
Yes.
And the function accepts it, completely unaware that it's empty. So as the execution enters the function body, the code needs to query the database. It calls ctx.value, attempting to retrieve the database connection.
And because the context is empty, that lookup returns nil.
Just nothingness.
Nothingness. And this is where the structural collapse occurs. The function now possesses a nil value, but the business logic expects a functional database pointer.
So what happens next?
Well, in Go, to convert that generic untyped value back into a usable database connection, Ethan's code has to perform a type assertion.
Which is like saying what exactly?
It essentially tells the runtime, hey, I assert that this generic value I pulled from the context is actually a pointer to a SQL database.
But you cannot assert that nothingness is a concrete piece of infrastructure.
You really can't. When you attempt a type assertion on a nil value, or assert the wrong type entirely, and you don't explicitly handle the error checking,
the Go runtime completely panics.
Yes. And if we connect this to the bigger picture, a runtime panic in Go is not just some minor glitch.
Right, it's not just a little warning pop-up.
No, it is a catastrophic failure that unwinds the call stack. Unless that panic is explicitly caught and recovered further up the chain, which, by the way, is highly problematic for core infrastructure logic, the entire Go routine crashes.
And frequently, the entire application process dies with it.
Exactly.
So just because Ethan wanted his code to look a little cleaner on the screen, a developer wanting a routine test causes a fatal memory violation.
Which is bad enough.
Right. And in a production environment, If a downstream service forgets to inject that exact database dependency into the context before calling Ethan's billing handler, active user requests are going to trigger process-level crashes at, like, 3.0 URM.
It's a nightmare scenario. He basically traded the safety of an immediate, predictable compiler error for the chaos of a deferred runtime panic.
That is a terrible trade.
It is. Furthermore, Eleanor points out that this absolutely ruins discoverability.
Oh, right. Think about a new person joining the team.
Exactly. If a new engineer joins the team and needs to use the billing service, they look at the function signature and see process bill, requiring a context and an amount.
What's simple enough?
But there's zero indication that they need to preload the context with a database, a logger, and a metrics client.
So how do they even find out?
The only way the new engineer learns about these hidden requirements is by running the code, watching it crash, and then forensically dissecting the source code of the process bill function to see what it was secretly trying to pull out of that magic bag.
That sounds incredibly frustrating. So, okay, the implicit approach is a total failure. The magic bag crashes the program, it sabotages automated testing, and it completely lies to future developers.
It fails on all fronts.
Right. But Eleanor isn't just going to lecture him, right? She actually has to refactor the architecture.
She has to fix the mess.
Yeah. So how does she actually rebuild this code to maintain some level of cleanliness without sacrificing that explicit contract we've been talking about?
Well, first she strips away all those dangerous type assertions, and then she introduces a foundational architectural pattern: dependency injection.
Okay, dependency injection.
Specifically via struct receivers. So instead of expecting the database and logger to be passed down through the arguments of every single function call.
Which was Ethan's original complaint, right?
Right. And instead of hiding them in the context, she creates a dedicated struct. Perhaps she calls it billing service.
And for you listening, just a quick refresher, a struct being a composite data type that groups related variables together.
Precisely. She defines the billing service struct, and inside it, she explicitly declares the core dependencies as fields.
So a pointer to the SQL database, a pointer to the logger, the metrics client.
Exactly. Then she writes a constructor function, usually named something like new billing service.
Okay, so the constructor function acts as kind of a gatekeeper.
That's a good way to put it.
So when the application starts up, the main function has to call new billing service, and that constructor explicitly demands the database and logger as arguments to build the struct in the first place.
Yes, the burden of supplying the infrastructure is shifted to the initialization phase of the application.
Do it once at the start.
Right. Once the billing service struct is successfully built and populated with its dependencies, Eleanor attaches the process bill function to that struct as a method.
So what does this all mean? Let's rethink that messy workbench analogy from earlier.
Let's hear it.
Instead of throwing everything into a dark duffel bag, Eleanor is basically constructing a customized, highly organized tool belt.
I like that. The billing service struct is the tool belt.
Exactly. So during the morning shift, which is the initialization phase, the worker is explicitly handed the hammer, the wrench, and the multimeter. And those tools are securely locked into the tool belt.
They're ready to go.
Right. The worker wears that tool belt all day. Because the tools are attached to the belt, the worker doesn't need to ask for a hammer every single time they approach a new task.
And how does that change the actual execution of the task?
Well, when it is time to process a bill, the function signature only asks for the raw materials specific to that exact job. It asks for the context and the billing amount.
Imperials.
Yes. It doesn't need to ask for the database because the function is attached to the struct, meaning it can simply reach down to its tool belt and grab the database whenever it needs to execute a query.
It's brilliant. The design achieves both goals simultaneously.
It really does.
The function signature at the execution level remains incredibly clean and focused purely on the business data, the amount. But the dependencies are no longer hidden or implicit.
Because they're in the struct.
Right. The compiler statically guarantees that the billing service cannot even be instantiated without the database. The contract is restored.
No more guessing.
No guessing, no type asserting untyped values, and absolutely no runtime panics caused by missing infrastructure.
So the dependencies are safely bound to the state of the application, leaving the function arguments reserved for the behavior of the application.
Exactly.
But, this leaves Ethan staring at a very obvious architectural remnant.
The context parameter.
Yes. Eleanor has moved the database and logger to the struct. She has moved the business data, the billing amount, to explicit arguments. Yet the context parameter is still sitting there as the very first argument in the process bill function signature.
Sitting right there at the front.
Right. And it is completely empty of infrastructure now. So Ethan rightfully asks, is putting dependencies in the context is a dangerous anti-pattern? Why does context dot with value even exist in the standard library?
It's the logical next question.
Mm.
And Eleanor answers this by laying down what she calls the architect's rule for context values.
Oh, the architect's rule. I love a good rule.
It provides a definitive boundary line for software design. The rule dictates that if your function cannot successfully execute its core business logic without the value,
Okay.
then that value absolutely does not belong in the context, period.
Wow. Period. So the core logic requires explicit, verifiable dependencies.
Always.
Like, you cannot process a financial transaction without communicating with the database. Therefore, the database's core logic. It fails the architect's rule.
Exactly. Ethan follows that logic logically.
Hmm.
If the database's core logic, what actually qualifies to be placed in the context bag?
Right, what's allowed in there?
Eleanor defines context values as being strictly reserved for request-scoped metadata.
Here's where it gets really interesting. Because the boundary between core operational logic and request-scoped metadata is where so many engineering teams stumble.
It's a very fuzzy line for a lot of people.
It is. Metadata is data about the data. Aaron Rose's article provides concrete examples of what actually belongs in that context parameter, starting with trace IDs for distributed systems.
Trace IDs are perhaps the most vital use case for context dot with value in modern microservice architectures.
Trace IDs. Okay, so we're talking about distributed systems where a single client request, like a user clicking checkout on a website, bounces through like an API gateway, an inventory service, a payment gateway, and a shipping service.
It touches a lot of different servers.
Right.
Right.
We need a continuous thread to stitch the disparate server logs together so we can follow the exact path of that specific checkout request.
That is exactly the mechanism. When the API gateway receives the initial click, it generates a unique alphanumeric string, the trace ID. It injects that ID into the context. As the request travels from the inventory service to the payment service, they pass that same context along. Each service can pull the trace ID out of the context and append it to their local log entries.
But the crucial distinction here, and this goes back to the architect's rule, is that the payment service does not require the trace ID to charge the credit card.
Precisely. The core business logic of charging the card relies on the database and the billing amount.
Not the trace ID.
Right. If the context is somehow stripped of the trace ID along the way, the logging system might fail to properly categorize the transaction in the observability dashboard.
Which is annoying, but
But the user still gets charged. The business function survives.
that makes total sense. The article also mentions things like incoming IP addresses for telemetry or authentication tokens intercepted by middleware.
Middleware interception is a perfect example of request-scoped metadata. Well, before a request ever reaches the core billing logic, a middleware function might inspect the HTTP headers, extract an authentication token, validate it, and then place the parsed user identity into the context.
Okay, let's apply our tracking mechanism analogy to this.
Go for it.
If the core logic is the actual credit card payment being processed on a factory conveyor belt, the metadata in the context, like the trace ID, the telemetry tags, is just the routing sticker slapped onto the outside of the shipping box.
I love that. The routing sticker does not affect the contents of the box.
Right. The payment processing machine at the end of the line doesn't need to read the routing sticker to charge the card. It just needs the tools on its tool belt and the specific payment data inside the box.
Exactly.
Now, a localized scanner further down the conveyor belt might read that sticker just to record that the box passed through zone 4 at 2.0 BM for, like, observability metrics.
Sure.
But if the sticker falls off, the system doesn't panic and shut down the entire warehouse. The core operation completes successfully.
And Ethan finally has his epiphany in the library.
It all clicks for him.
It does. He synthesizes the entire lesson. Dependencies are explicit, ensuring the system can process the request safely. Metadata is implicit, allowing the system to observe and route the request without cluttering the business logic.
It is such a profound realization about systemic boundaries. You keep the magic bag closed to the things that matter for survival?
Yes. You let your system's contracts tell the absolute truth to the compiler and to your fellow engineers.
Transparency must always take precedence over false simplicity.
Always.
And, it is a lesson that extends far beyond writing Go code. Whether you are architecting a back-end microservice, designing a workflow handoff for a marketing department, or just communicating logistical requirements to your team, keeping your contracts explicit prevents catastrophic downstream failures.
It's universal.
It really is. When you hand someone a magic bag and implicitly expect them to guess the hidden requirements necessary to succeed, you are setting the entire system up for a runtime panic. Construct the tool belt, clearly define the raw materials required, and ensure the signature of your communication matches the reality of the task.
This raises an important question, particularly when we consider the rapidly shifting landscape of how software is actively being generated and maintained today.
Oh, you mean the integration of large language models and AI agents into the architecture process?
Exactly. We are entering an era where AI systems are reviewing, refactoring, and generating massive portions of enterprise code bases.
Which changes everything.
It does. Because an AI agent does not suffer from the same cognitive constraints as Ethan. It has an immense context window. It can hold the entire repository in its active memory simultaneously.
Which means the AI possesses a nearly flawless map of the implicit architecture.
Yes. It instantly knows every hidden dependency tucked away inside the magic bag across thousands of files.
It doesn't struggle to remember that the process build function secretly requires a database pointer buried in the context.
Therefore, an AI might analyze context dot with value and determine it is actually a highly efficient pattern.
Wait, really?
Think about it. It saves token space in the function signature, and the AI never loses track of the hidden infrastructure. To a machine, the magic bag is perfectly legible.
Wow. But the code base doesn't exist solely for the machine. It exists for the human engineers who have to debug it at 3 a.m. when the AI's logic creates some unforeseen edge case.
Exactly.
If we allow our architecture to drift toward implicit hidden complexities simply because our automated tools can instantly parse them, we are trading our own architectural agency for immediate convenience.
It's a dangerous path.
We are building a perfectly minimalist kitchen where only the robotic chef knows which cabinet holds the spatulas. And if the system breaks down and the human engineers cannot read the map because the contracts are full of lies, we lose complete control over our own infrastructure.
A very sobering thought.
It is. That is definitely something to deeply consider the next time you find yourself tempted to sweep all of your structural mess into a tidy, opaque container just to keep the screen looking clean. Keep those contracts explicit, folks. Maintain your agency. Until next time.